So it's looking more and more like um, the work that I'm interested in with respect to OSLF ends up pivoting around this idea that for every notion of computation, there's one or more sort of good data structures, and that ends up informing the relationship between computation and logic. So let me say more specifically in terms of OSL itself. So the core motivating examples that I've gone over many times with the OSLF program clearly demarcate a boundary between the logic of collection and the logic of structure. However, there's an interdependence between the two. Specifically, whatever notion of collection you've got, that's going to dictate the expressive power and the ambient theory that you use to codify the computational model. So, for example, if your notion of collection is set, then that comes with products and other things, and as a result, you can express Levere theories. If your notion is linear, then you can't express a Levere theory, right? You might be able to do a prop, but so there's and so there's this clear limitation or connection going that direction. Likewise, you want to be able to encode the notion of collection into the computational structures, and that has to also be consistent with the notion of collections with the ambient theory, where hopefully all this is being hosted. So there's a way to address the circularity where your notion of collection has got to be is impinging upon your notion of computation. Your notion of computation is impinging upon the notion of collection, right? So as with the row calculus, we just embrace the circularity and take advantage of it. So the trick, and I mentioned this last time, but now let's get a little bit more specific. The trick is we think of the collections as layered. So at the core, we have something that's at least a monad. So it supports unit and flatten and map. And so with this, we can build a notion of comprehension that uses a variant of the Mitchell-Benabou language. So it's this is in some ways Wadler's comprehending monads is foreshadows this, but he doesn't work out the details. Mike and I worked out the details of a notion of comprehension that that just uses the discipline of the monad interface. And what we're going to do is we're going to extend this by allowing computations over comprehensions. So now we can say that a collection is either extensional or it's intentional. An extensional collection is going to be a comprehension that just lists out 0 or more terms, right? And we don't know, these squirrely braces are not necessarily set, right? We're building a comprehension in some monad, which is effectively given by C. So the core of C is the monad. And then we have the intentional collection. So these we're giving the collection by hand. Here we're building it computationally. So there's some term in the programming language that has potentially some variables in it. Those variables are going to be substituted by some values. The values are going to be drawn from some other comprehensions and satisfy a given predicate, where the predicate is going to ultimately be expressed in terms of the logic that we're generating, right? So you see there's lots and lots of circularity here, and what we're doing is sorting out all of the different circular arrows and how they ground out. Does this make sense? At least following roughly what we're doing here?
Yes.
Good, good, good. Okay. So if we were to apply this to linear collections, what we'd need is some kind of data structure that's like a linear set. So Masaru Shirahata investigated linear set theory. And when we analyze this, we see that there's a, sort of it grounds out in a translation, or transliteration probably is a better way of saying it, of the axioms of Zf itself. So let's just take a look at Zf. So here are the axioms of Zf. It's a tiny handful of axioms. So this is allegedly at the core of the foundation of mathematics, right? So nice, crisp, simple axioms on which we build all of mathematics. So let's talk about what these axioms mean. So extension just says collections are going to be equal if they have the same contents. Empty says that there is an empty collection. Pair says that you can make a collection that contains two elements. Union is flattened. If you go through this carefully, it's really just flattening of collections. Power says that there's a canonical collection of all collections. So we'll return to this one in a bit. Separation is filtering. So, in terms of Scala collections, this is mapping with a predicate. Infinity says that there's at least an infinite collection. Regularity, also called foundation, says that collections ground out. They're not circular. We know that it's sometimes useful to have circular collections, so that is arguably something that we could relax as well. And then replacement is map. Already the notion of monad is getting us pretty far, right? So monad is getting us replacement, and if it's a monad, replacement. If you're careful, you can also get separation. You can get if you have monad plus, you get the empty. Extensionality is separate, but the notion of monad is coming close to covering the surface area here, or increasingly refined notions of monad. Now, the one thing about monads that is very different here is that what goes into a monad stays in a monad, right? So it's just like Vegas. What happens in Vegas stays in Vegas. So what happens in a monad stays in the monad. You send computation into a monad, you don't get results out necessarily with just that interface. You have to enrich it. So sets have an element of predicate, and we'll want to return to that in just a moment. In particular, if we modified the element, so if we enrich our notion of collection to be a monad plus an element of relation, then we need to ask about what is the signature of the element of relation. So in general, you could have a signature of the element of relation be take an element, take a collection, and return not a Boolean, but some truth value, say T. So whatever your domain of truth values are, and they could be the truth values of linear logic, they could be the natural numbers, they could be the unit interval. So all of these, what they do is they don't tell you the position of the element. And because they don't tell you the position of the element, that's why all of these are unordered. So all of these are going to be very set-like. But you could do better. You could in fact build a zipper. So if the collection is a monad, that means it has some underlying endofunctor, which is in most cases going to be differentiable. So we can build a notion of a position using the zipper ideas. So you could have element of return the position and a truth value. Then you impose equations on the positions to recover the unordered things. But now you can have ordered things like lists and fuzzy lists and things like that. Once you have position, though, power is no longer definable. And the reason is because as soon as you have a total order, when you take the sub collections of a given collection, some of them will not be comparable. So either you need to impose a notion of well ordering, some kind of order comparison. So that would be adding a notion of choice to your mathematics, or you would have to you'd have to have some kind of partial order. So so now we're starting to see a unification. So all of this structure here is expressible in terms of a more abstract characterization than just sets. And so this is what we're marching towards, is a crisp, abstract characterization of collections that will give us sort of the right changes on logic, so the logic collection connection, so to speak, so that we can so that we can clearly sort out this recursion here between collection and computational structure. Right, so that's the name of the game, and it seems quite doable, right? We can. I haven't proposed an interface yet, but I think it's fairly straightforward to propose such an interface. It's basically, it starts with monad as the core. We add a few axioms, so it becomes at least monad plus, and then monad plus together with some kind of element of relation. And that gets you most everything here. You would have to add extensionality that's independent. You would have to add regularity that's independent, but everything else, so extensionality, regularity are independent. And then monad plus with element of give you everything, and then you get power if and only if you have either a some notion of choice, or you have a partial order as opposed to a total order. So that gives you a notion of collection, which you can then plug into this notion of comprehensions. And now you have that sorts out the set of links between the notion of collection and the notion of logic. So the notion of logic will exactly mirror whatever your collection semantics are. So whatever your operations for collections are, that will be the logical operations that allow you to define the fees, these things here, and that ends up tying up all the loops. Does that make sense? Any questions?
I think I can follow. So this fee here is like a predicate, and it doesn't have to return only true false, right?
That's correct. It can return whatever your truth values are, and then what you'll get is you'll get buckets, right? You'll get so let's say you have the natural numbers, so you'll get a bucket of terms that are associated with 0, a bucket of terms that are associated with 1, a bucket of terms that are associated with 2, and so on. Or another way to slice and dice it is, you can put the tag here. So you can tag them with the truth value. So you either have a product or you have a co-product. Does that make sense?
Yes. Yes.
Cool. So I mean, to me, what's really interesting here is that we now have not just one mathematics. We've got a wide variety of mathematics, right? So what's going on here is this is the foundation of math. This is like all of mathematics, is built this way. At least, you can always replace this with category theory, but the current accepted consensus is ZF is the foundation of math, and then you make a decision as to whether you're going to be constructive and include choice or not. That's the mathematical ground. And what we're saying is, well, this ground can actually be parameterized, so that we get this lots of different kinds of mathematics, that where you have this relationship between the logic that's used to express these algorithms and the data structure that is used to model these, give a model to the formulae. They're dual to each other. You have a logical view, you have a data view, a model view, and they're recursively defined. And that's your foundations. So you get not one maths, but many maths.
So this means that for this kind of axioms, set is most appropriate collection.
For these, yes.
For these, yeah.
Yeah. But you can now define an API, right, which effectively gives you these capabilities, and then you can or if it doesn't give you these capabilities, you have either analogs or you say why you jettison them. So in the case of power, if you have an ordered collection and you don't want choice, if you have a totally ordered collection and you don't want choice, then power is off the table. You can't build a power object. If you have a partially ordered collection, then you can put power back on the table. If you add choice or well ordering, then you can put power back on the table, if you have an ordered collection.
And can we say that this is directly connected to representation of if we are thinking about some kind of rewrite rules, eventually we will think about how what kind of collection do we need to represent all these rewrite transformations.
Yeah, I mean the rewrite stuff we're modeling as an expansion of the structural theory of computation with the theory of a graph, right? That's the way we're modeling it right now. So you have some structural theory like a Levier theory or a higher order algebraic theory, one of those kinds of things. So either you have variables in your notion of computation or you don't, right? So if you have variables, then you have some kind of higher order algebraic theory that gives you your structure. And then your rewrite rules, you say, what are the sources and targets for a given rewrite? So like in the case of application, a lambda term that has an abstraction in the head position and some arguments. Then you do the beta reduction where you apply the substitution, right? So the source of the rewrite is the the application, and the target of the rewrite is the beta reduced term. So that's the that's how you introduce the rewrites into this. Does that make sense?
Yes, and when you when you present this this relation between collection and computation, are you thinking about rewrite or?
Yeah, so the place where that shows up is right here. And so what we're saying is we're building terms, and you can introduce the rewrite right here. So instead of building the term and leaving it, like if you have a reducible term, you can have the intention, actually take the target of the rewrite that applies to this term.
I see. I see. So we are building terms here, but not. This is not a definition also for rewrites.
You can include the rewrites by having these reduce. If you don't have church roster, then you have questions you have to answer. Like in the case of lambda, no matter what reduction path, if it reduces, it's going to always reduce to the same thing, right? But in the case of row, you don't have that property. So you have to make some decisions as to what you do here. Anyway, so I think this is very, very exciting. Well, what we're providing is a completely different conception of the foundation of mathematics.
And hi, Greg. I have a question regarding the application of this. Is this a theoretical field for next iterations of Rowling?
So what this does is it allows us to build you hand us a model of computation. So these terms here, and you hand us some notion of collection. So these C's here, and we will build a logic. You can think of this as a type system that applies to your notion of computation. Actually, it'll apply to this whole surface area of computations extended with some notion of collection, right? And that type system, the type system that comes out of that algorithm, it has lots of good properties in the sense that you can use it to reason about security or reason about liveness or safety, blah blah blah. So if the notion of computation is Rowlang, then we'll get a type system for Rowlang. So it applies directly to Rowlang, but you could, instead of using Rowlang, you could hand me JavaScript. So now your terms are JavaScript terms, and we'll get a type system for JavaScript. You could also hand me the Java VM, so the Java bytecode. So your terms are Java bytecode. Well, actually, it's more than just the Java bytecode. It's a Java bytecode plus the state of the virtual machine. Your terms are some bytecode and a VM state, and we can generate a type system for that model of computation. This is highly general. Do you understand what I'm saying? Does that make sense?
Yes, I think so. And I guess it highly relates with behavioral type systems.
Yes. So what we're saying is that you get a class of behavioral type systems this way. And it's a very broad class. In fact, we can describe both session types, multi-party session types, and the Kyrie style types within the system.
Okay, thanks.
Sure. Good question.
So we can have some kind of graph rewrite system, and we can also specify. We can also generate a type system if we specify how we what kind of rules of rewrite rules we have.
Yes, in principle, that's the case. So far, we have only applied this to syntactic, models of computation. So if you have complicated graphs that you're rewriting and complicated graph rewrite rules, there may be things that you want to look at with respect to this algorithm. For simple graphs, like the kind of DAG structures that you get with the mobile process calculi, it's not a problem. But you could have all kinds of crazy loopy graphs that you're rewriting, and in that case, you want to check that this algorithm still applies.
For example, ZX calculus will definitely create some kind of complicated graph structure, right?
No, that's not super complicated. The ZX calculus they're all planar.
So when you say simple, do you mean there is a finite number of transitions or infinite?
No. I mean, I'm not worried about that. What I'm worried about is, imagine that your graph is not planar, right? So your graph describes some kind of weird knot in 3 space.
I see. So is this relates to higher order transformations or?
No, not necessarily. Not necessarily. It's just that, as soon as you go, like, terms are trees, right? That's why you have what's called a syntax tree, right? So as soon as you go outside of trees, and let's say you go outside of planar graphs, right? So now you have really, really potentially hairy, complicated graphs. You just want to make sure that any of that knotting and looping doesn't mess up the way we've modeled things here, right? There could be some strangeness in the way you pull the graph structure through the collection structure that we haven't thought about, right? Because now you have dependencies that look funny. So yeah. So anyway, I mean, it could work. I just, I've restricted it's already hard enough with term rewrites, and term rewrites get me lots and lots of stuff. Right. I mean, I like all the modern programming languages I can do with term rewrites.
So you're saying that if we have some DAG structure, this is like very simple.
The DAG is no problem. Yeah. Yeah. I'm just worried if your graphs are knotted and loopy, then you just want to check some details.
And ZX calculus is more complicated than a DAG.
Yes, but it's still planar. They're still temporally lead.
Can you explain what this means?
Yeah, you don't. There's no knots, right? It lies in a plane. Any other questions?
Can you say something about the relation between collection and I'm not sure how to formulate the question, but connection between computation and some kind of when we have rewrites, we can basically connect all of the dots that are part of one step of rewrite. And can we somehow, is there some kind of connection to topological structure of this kind of rewrite system? Or I'm not sure.
I'm not sure I understand your question, to be honest. Can you give an example?
I was watching a presentation of Jonathan related to Wolfram model of multi-way graphs. So he was explaining how they have notion of a manifold that is connected to their rewrite rules, and my understanding is they only think about the X, and they have this manifold. They can say if some rewrite rules ends up with on the same place, they're not changing this manifold, and the only difference is like there is a longer path to get to the same point.
I don't know what it means to. I thought at first I thought you were saying you were rewriting the structure of the manifold, but now I don't know how the rewrite. But once you've said more, I don't understand how the rewrite rule is connected to the manifold.
So they start with some simple graph that they want to and some simple graph and some simple rewrite rules.
So the rewrite rules are applying to graphs.
Yes.
Okay. All right. Great. So you have a big graph rewrite system. How is that related to a manifold?
So after one step, or after each step, they connect all of the positions of all of the rewrites. And they're
locations within the graph.
Locations of the graph. Yeah. Yeah.
Okay, but so this is a little bit counterintuitive. Usually the rewrite rewrites the whole graph. What does it mean to what is the notion of position being offered here?
So they have term folations. I'm not exactly sure what this is, but
maybe if you want to send me a link, I could take a look at it and I could answer your question after taking a look at it.
Yes, I can send you the link. I mean, it is interesting because
in general, you can use the zipper as a notion of location within a graph.
I see.
But
yeah, I was thinking, yeah.
Mm-hmm. Yeah. I don't know how foliations are related to the graph in this case.
So they were using ZX calculus to prove something about their rewrite system. So I was wondering how OSLF can also.
Well, you can directly apply OSLF to the ZX calculus. That's not a problem. Again, and the reason is because the graphs they lie in a plane.
From their perspective, they're saying that ZX calculus is too large to for their perspective to analyze, because they have infinite rewrite rules, and they're only looking at simple transformations. So they were using only part of the ZX calculus.
Yeah, the ZX rewrite rules are rewrite schemes. Yeah. But that I mean, it still just gives you a graph. Mm-hmm. So you can model the rewrites in the way that where you have what we are calling a graph homomorphic model, where you add the theory of a graph to your theory of term structure, or rewrite structure. Whatever structure you're using to rewrite, you add to that theory the theory of graph, where your source and targets are the red X and reduced expressions. Cool. I mean, I'd love to know more about the other thing, but I don't quite get it yet. Any other questions? Thank you very much for your time and attention. I appreciate your willingness to engage this material.
Thank you.
Thanks.